Hey everybody, welcome to the second lesson of the week. Everything we've looked at so far with respect to curved mirrors has been qualitative. So we've been doing our ray diagrams. We've been looking at how to describe our images using lost. Now we're going to move more to a quantitative state here. So when we're talking about quantitative features, we're looking at actual calculations. So what are the actual values? When I say something is closer, well, how much closer? Like, what is the actual measurement? So there are two equations that we use for mirrors, and they're found up at the top here. So the first one is 1 over f is equal to 1 over di plus 1 over do, where f is your focal length, so the distance between the focus and the vertex. Di is the distance that the image is from the vertex. Do is the distance that the object is from the vertex. And there's a second equation which actually has some hidden equations in it. So the second one is m, which is magnification, so how magnified is the object, which is equal to hi over ho, which is equal to negative di over do. So di and do are the same as the first equation, distance that the image is, distance that the object is. Hi and ho deal with the height. So how high is the first image and how high is the object? And then magnification. But there's a couple of equations hidden inside. You'll notice that there's two equal signs. So if I cover up, for example, negative di over do, then it just becomes magnification is equal to hi over ho. Or if I cover up hi over ho, then magnification is equal to negative di over do. Or if I cover magnification, I can get hi over ho is equal to negative di over do. And so there's a lot of versatility in these equations in that you can use them to do a lot of different things. So as with any word problem, I always like to write down what I have in the word problem. So without any further ado, let's actually calculate this out. So it says here, determine the image distance in each of the following. So I'm going to be looking for, in this particular case, di. So I guess I'm doing this twice because there's two examples here with image distance. So if that's the case, I'm going to read the first question. It says here, a concave or converging mirror has a focal length of 15 centimeters. So I know my f value is 15 centimeters. So f, oops, I don't know why it's doing that. F is equal to 15 centimeters. And it says an object is placed 40 centimeters, so I have a DO is placed 40 centimeters from the mirror, so from the vertex. I'm looking for DI. So one of the hardest things that you guys are going to experience here is picking and choosing the right equations to use. So you're always going to want to pick and choose an equation that has just one variable missing. So if I'm looking at the information that's given in the question, I'm going to pick the first equation because I'm just missing the DI from the first equation. So that is a question mark. That's what we're trying to figure out. So here we go. Here's the solution for it. So I know that 1 over f is equal to 1 over di plus 1 over do. Now I know a lot of people hate fractions, but we're going to have to deal with some fractions, but I got an easy way on how to deal with it. So 1 over my f value, which is 15, and by the way, I should mention that in the question here, it's given, everything is given in centimeters. If they are given in different units, you got to pick a unit and stick to it. So it's either, if I give it to you, for example, in centimeters and meters, then that means that you got to choose one. Either put everything into meters or put everything into centimeters. So in this case, we'll just leave everything in centimeters, so I'm not going to bother writing them down in the equations here, so we'll just keep it a little cleaner. So 1 over 15 is equal to 1 over di, which is what we're interested in finding. Remember, we're interested in the distance that the image is, plus 1 over do, which is 40 centimeters. And I said that I wasn't going to put it in the units, but I did. In any case, I need to solve for di. So I'm going to bring 1 over 40 over to the other side. So now I have 1 over 15 minus 1 over 40 is equal to 1 over di. I need to find a common denominator if I'm adding and subtracting fractions. So the easiest thing for me to do is take the 40 that I have here, and I'm going to multiply top and bottom by 40 on the other fraction, and then I'm going to take the 15 that I have here and multiply top and bottom by 15. So I'm going to end up with 40 over 600. Let me get the pen working again. There we go, 600. Minus 15 over 600, which is equal to 1 over di. Now I can do 40 minus 15, that's 25 over 600. But you'll notice that that is equal to 1 over di. I don't want 1 over di, I just want di. So as a result of me just wanting di, I can flip both equations. So instead of 25 over 600, I'm going to do 600 over 25, which is equal to di over 1, which is just di. So then I can do some simple math. 600 over 25 is equal to 24, and that's in centimeters, is equal to di. So my image is 24 centimeters from my mirror. Now, let's think about if this makes sense. I'm going to do a quick sketch here of one of the ray diagrams that you guys had. So I know that it's a concave mirror. I know that my focal point is at 15 centimeters. I know that my center of curvature is at 30, and it says that my object is somewhere beyond that 30 at 40 centimeters, so somewhere over here. If I'm doing my ray diagram, I'm going to have my first line come across parallel. It's going to reflect through the focal point. My second one's going to go through the focal point, hit my mirror, reflect parallel to the principal axis in this direction, and it's going to cross somewhere around here. Now the image, pardon me, the object was at 40 centimeters. So this guy's at 40 centimeters. My image is at 24. Well, you notice that the focal point was at 15, so that's my F. And you'll notice that my center of curvature was at 30. So somewhere between 15 and 30, closer to 30, is 24. And that's where my image actually appears. So you'll notice that these things will correspond to our ray diagrams. Now, I did this question a little bit backwards in terms of how I normally do it. And I did that for a reason. We want to do the calculation first and then ultimately show you guys what it looks like in terms of a ray diagram. I always start with a sketch ray diagram because then I know whether my answer makes sense or not. So we're going to do that with the next question here. It says an object is placed in front of a concave mirror. So I'm going to draw my principal axis again. I'm going to draw my concave mirror. And it's placed 10 centimeters. So my object is placed somewhere around here. Let's say this is 10 centimeters from my mirror. That has a focal length of 15 centimeters. So my focal length is somewhere around here. So this is my F value, which means that my center of curvature is somewhere over here at 30 centimeters. So you'll recall this one is going to make the image appear much larger. So of course we have my first ray coming off. It's going to reflect through the focal point. My second one will leave the tip of the object as if it was coming from the focal point, strike the mirror, and go backwards in terms of parallel. And then, of course, as a result, we're able to produce an image somewhere here. So we're looking for a DI. Now you'll notice that the image in this particular case is behind the mirror. So the value we get for our DI should be negative. So let's work this out right now. So 1 over F is equal to 1 over DI plus 1 over DO. So 1 over 15 is equal to 1 over DI plus 1 over 10. Remember, those are the values that I had. So my focal length here was 15 centimeters, and my object distance was 10 centimeters. And I'm looking for DI again, so that's my question mark. So I'm going to do the same process. So I'm going to do 1 over 15 minus 1 over 10 is equal to 1 over DI. Of course, we need a common denominator here, and so I end up with 10 over 150 minus 15 over 150, which is equal to 1 over DI in this case. And then, of course, 10 less 15 is negative 5 over 150 is equal to 1 over DI. Now, of course, I said before I don't want DI. I don't want 1 over DI. I want DI. So I just take the reciprocal of both. I have 150 over negative 5 is equal to DI over 1, which is just DI. And if I do 150 and divide it by negative 5, I end up in a situation where I get negative 30 centimeters equals DI. And if you take a look at my image here, you'll notice that if I were to do the lost here, that the image would be farther from the vertex than the object is. So this agrees, with what I have discovered here. So let's try another one. Actually, pardon me, I forgot that there's a second part to the question that asks, what is the magnification? So obviously, if I'm asking for magnification, you have to use the second equation. So I know that magnification is equal to hi over ho, which is equal to negative di, pardon me, negative di. I don't know why my cursor keeps erasing from there. Di over do. We don't have anything to do with hi and ho here, so I'm just going to scrap that part. So now I have magnification is equal to negative di over do. I have di and do, I calculated them. So I have negative of negative 30 over my do value, which is 10. So negative 30 is just positive 30. 30 over 10, magnification is equal to 3 times. You'll notice that there is no units here because the units here are centimeters and the units here are centimeters. They will cancel each other out. So I have no units. It's just 3 times magnified. So my image here is 3 times the size of my object. So you'd find that if you were looking at like a makeup mirror or something like that. Okay, let's try another one. So it says here, a spherical polished metal ball is used as a diverging mirror. So diverging mirror is another name for a convex mirror over a bird bath. It says its focal length is minus 20 centimeters. Notice that the distance here is in negatives, which means it's behind the mirror. And it says a bird that is 25 centimeters tall, standing 50 centimeters from the metal ball, looks directly into the metal ball. How far from the metal ball does the image form? So in this case, I have my, I'm going to do my sketch here. I have my principal axis. I know it's a convex mirror. I know somewhere in front there is a bird placed at 50 centimeters. So the distance between the mirror itself, this distance is 50 centimeters. Now, this is not obviously a bird, it's an arrow, but let's just, for simplicity's sake, just put an arrow there. And then, of course, behind the mirror at 20 centimeters, we have our focal length. The pen is acting up, pardon me. So this distance is our focal length. And then, of course, twice that distance at 40 centimeters would be our center of curvature, our focal length. And so if I follow my rules, as I showed you guys in the previous lesson, my first ray leaves there, goes parallel, bounces off at this angle as if it was coming from the focal point. My second one is going to go towards the focal point, of course, bounce off parallel, and they're going to meet somewhere over here. So I'm going to produce this tiny little arrow over here, somewhere closer than my focal length, so somewhere closer than the 20 centimeters. So we got to make sure that when we actually calculate this out, it agrees with our ray diagram, which we know is correct. So in this case, it's asking you how far does the image form. So again, I'm looking for di. So 1 over f is equal to 1 over di plus 1 over do. Watch your negatives here because we got to make sure that we are paying attention to those negatives because that'll tell us which side of the mirror things are actually on. So 1 over negative 20, which is my focal length, is equal to 1 over di, which is what we're interested in, plus 1 over 50, okay, because our bird is 50 centimeters from the mirror. So I'm going to bring that over, so I have 1 over negative 20 minus 1 over 50 is going to be equal to 1 over di. Of course, we want to make our fractions easy, so we multiply top and bottom. So I have 50 over negative 1,000 minus 20 over, pardon me, 1,000. Remember, it's the common denominator there. And that's equal to 1 over di. And then from there, I'm able to then do my actual math. So negative 50 minus 20 is negative 70 over 1,000 is equal to 1 over di. But again, as I mentioned in the previous questions, we're not interested in di. We are not interested in 1 over di, we're interested in di. So 1,000 over negative 70 is equal to di. And when I do the math, I end up with a negative 14.26 centimeters is equaling to di. which agrees with our image that we drew up there. So we know it's closer than 20, we know it's behind the mirror, so it's going to produce a negative value here. So that's good, that agrees. This agrees with our findings. So if I go down to the last one, it says, what is the size of the image? Now, I had already written this out. So it's what is the size of the image? In other words, we're interested in finding HI. So in the question up above, it gave us the height of the bird. The bird was 25 centimeters. So I'm just going to use this part of the equation. Notice I've canceled out my magnification. I've got rid of that because it's not asked me for it. So I know that HI over HO is equal to the negative DI over DO. So all I'm doing is plugging values in and solving. So HI is what I'm looking for, and you guys, I'll do this in red here. I'm looking for HI. I'm given my 25 centimeters, which is the height of my bird. I know that the image that my distance is, which I just calculated in the previous part of the question, is negative 14.26, and I divide that by 50 because that's the distance that the object is. When I take the 25 and move it up, I can then solve for the value, and I get an HI of 7.13, which is what we would expect. We would expect that the image would be very, very, very small, because that's what usually happens in these convex mirrors. You'll also notice that the sign in front of the H is positive, which means that it's an upright image. And so I've given you a little bit of a cheat sheet over here. If your DI is positive, it means you're in front of the mirror. If it's negative, it means you're behind the mirror. If your HI is positive, it means you're upright. If your HI is negative, it means you're inverted. And if your magnification is positive, it means you're upright, as we found up above. If your magnification is negative, it means that you have an inverted image. So this is a really easy cheat sheet. Oh, pardon me, I forgot. There's one more focal point. If your focal point is positive, it's in front of the mirror. If it's negative, it's behind the mirror. I should also mention that there are going to be questions in the practice where I don't tell you whether it's positive or negative. You got to look at the type of mirror that I have. So if I have a convex mirror, my focal length is negative. If I have a concave mirror, it's going to be positive. So be very careful. I'll put a little star next to that so you remind yourselves. So that's how we use our magnification equations, and we're able to solve mathematically for the quantitative actual values of either heights, distances, or magnification. So I hope that was an easy enough lesson for you guys. If you guys have any questions, please email me and we'll go from there. Thanks, guys. See ya.